Hi, my name's Peter Sorensen. Thank you very much for attending this session on changing climate and changing waters. I'm a professor at the University of Minnesota, where I've been for just over 30 years now. My expertise lies in fish biology, fish physiology in particular, that of invasive species such as carp, for which some of you may know some of my work. Which is also involved water quality. But today I'm going to talk with you about an issue that I've become convinced is really the defining issue of our time, at least as it pertains to fresh water. Great many issues challenge waters in Minnesota, as you all very well know. Amongst these are poor water quality, flooding, quantity of water, habitat loss in the water, declining fisheries, declining biodiversity. Of course, these are all highly interrelated, and there's no easy solutions to any of them. So today I thought I'd share a little story with you about some research we're actually still conducting on a big-headed carp, or Asian carp, from Asia. These fish were unfortunately introduced into our waters in Arkansas in the late 1970s and have been swimming up the Mississippi River ever since, challenging lower Mississippi now, where it first enters Minnesota. About 2 years ago, my lab was fortunate enough to receive a $1 million grant from the state, LCCMR, which we're thankful to, for developing a sound deterrent for carps at Lock and Dam 8 on the edge of border of Iowa and Minnesota. And we, after some efforts, we actually installed that a year ago, and we're testing it last summer in 2019. And during this time, there was considerable flooding, which was really, frankly, a great annoyance and challenge at the time. But we persisted with our studies, had some somewhat positive results, but nevertheless, we're very disappointed to find out that in March of this past year, March 2020, 41 adult silver carp were caught in one haul just a few miles upstream of our deterrent system. So of course I wanted to know what that was all about. And looking back on it, we started to look at patterns in the river and wet water. And what we realized pretty quickly, we thought it was a very warm and wet year and there was notable flooding, but we hadn't realized it was frankly one of the warmest and wettest years of the past century. And that's evident right here in this precipitation pattern, which almost bullseye right into our test site here, in which many inches more rain were received than normal after a very warm spring with extensive runoff and melting. And of course, these all caused the rivers to rise, flooding out locks and dams along the river. And of course, when you have a flooded lock and dam, a fish can simply swim around it. And frankly, felt pretty foolish about it, particularly when we started to look at how these patterns of weather in 2019 fit in. Was wondering if this was really a true anomaly or something more different than that. And it turned out it really was a part of a fairly predictable pattern that dates back at least a century. Minnesota's been collecting good data since the late 1800s, believe it or not. And during that time, almost 4 to 6 inches more of rain, particularly in the southeast corner, has fallen on our state every year, of course, with some variation, while there's been considerable warming. And this has particularly occurred, as I unfortunately found out, particularly it's quite striking, 6 or 7 degree changes in maximum temperatures in February and March in Minnesota. These are very extreme. And this is averaged out by state climatology office from good records over the past century. So we had put a lock and dam in place for $1 million, frankly, in a place that was very susceptible to flooding, which was becoming part of a predictable pattern. Looking at that, as a scientist in particular, I wondered how predictable this really was and what was causing it. And as you might imagine from the title of the talk, it turns out it's entirely, absolutely, perfectly in line with climate change. And basically, the theory of climate change, I'm sure you've heard it all. I would say the facts of climate change, which were established over a century ago by Svante Arrhenius in 1903, who got a Nobel Prize for understanding the effects of carbon dioxide in the atmosphere on our climate. Svante realized that the only way he could explain the great ice ages in Europe 10,000 years ago was elevated CO2, in this case from volcanism. And it was CO2 that was the culprit. But he also realized remarkably that human beings were putting quite a bit into the atmosphere. And he accurately predicted 4 to 5 degree temperature change based on his estimates of CO2 release. Since that time, of course, we've started measuring CO2, and that's what you see here from Mauna Loa in Hawaii, and it goes up every single frickin' year, and is now well over 4,400 parts per million. And all the data from the lab and the field, hundreds and hundreds of studies show that this necessarily results in a warming phenomenon, and that's what we're seeing. So my conclusion, after, I'm embarrassed to say, spending $1 million instead, or I haven't quite spent it all, quite a bit of state funding, is that really, if we're going to control aquatic invasive species in particular, we really have to factor in climate change, warming and flooding in our waters, or it's all for naught. So that's kind of end of my first part of my talk. So now I'd like to suggest to you what you might want to consider, maybe, so hopefully you can learn from my hard lesson there. And I thought I would start with just sharing a few facts of what we know about climate change on fresh water. And you hear quite a bit on marine waters, but very little on fresh water. And this puzzles me, and that's kind of what I'm dedicating myself to right now. So I'll go through about half a dozen facts on effects of warming and CO2 on our waters, and then first the bad ones and then some good ones, and I'll present some good opportunities that you all have. The first fact is that, like it or not, no matter what we do, when we look at the data, and this is data that's been produced now for about 50-something years, we can determine how much CO2 is in the atmosphere. It adds up with how much is released, and it adds up and directly predicts and coincides with temperature rises in the atmosphere. And we've already seen about a 1.5 degree rise Fahrenheit, or about a degree Celsius. And even if all the CO2 were to stop being released today, this will undoubtedly continue. And we're going to be looking, and we'll come back to this, at least a degree Celsius increase. And if we don't get smarter about this and change our ways, it will be far worse. But let's just look at this scenario now. Many people are worried about this. I'm worried about this, and I'll show you why in a second. The second factor is that obviously the atmosphere is warming, and the atmosphere is warming, and as it warms, of course, it necessarily, physics states, just molecular movement, that the waters that underlie the atmosphere are also going to warm. And here we see some data from Lake Superior. This is the best data I could get from this region in waters, which are more complicated because freeze-thaw cycles. But you can see Lake Superior's come up actually disproportionately in that period of time, more than the air around it. Some of you may be totally familiar with this. I apologize if you are. In addition, and that's what this figure is here, dates of ice cover, days of ice cover are also reduced. Okay, these are important. Now, why is that important? This maybe you know, or maybe you don't know, but one reason is that water contains very little oxygen. You may not, this is not intuitive to a lot of people, but the amount of oxygen in water is only about 1/20th of that in air. So about 20% of the air that we breathe is oxygen. In contrast, by weight, only about 5% of same amount of oxygen is in water. And furthermore, as water warms, and this is what this figure is showing, this is dissolved oxygen per temperature in fresh water, it drops dramatically. It's almost a linear trend. So as water warms, it is less able, this is just simple physics, to retain oxygen. The other fact, I'm sure you're absolutely aware of this, but I just wanted to point it out, is that the animals that live in our waters, at least around here, we don't have any marine mammals, are mostly fish and snails and things like that. And they're all poikiotherms, which means they're cold-blooded, which means that a fish automatically, necessarily, within milliseconds, assumes the temperature of the water around it because it passes through its gills. And of course, these fish also need oxygen. But my main point is that they have temperature optima that they all exist at, and that's what this is showing here. So in northern, well, let's look at a lake whitefish. You can see its temperature optimum is around 15 degrees Celsius, which is maybe 65 Fahrenheit. If you get too warm, it doesn't grow. Just a couple degrees warmer, it's already going down. Too cold, it's going down. So all these fish have evolved to be very, very good fits with the local environment. So you could see where I'm going, I think, and that means that unlike people, we just put on a jacket or something if it's too cold, we take off a layer if it's too warm. Fish are living the experience, man. They're in it. So as water's warm, even just a little bit, they're going to start to run out of oxygen, which means they're going to grow less. And that's what this figure is showing here. Necessarily, fish will get smaller as our water's warm. They don't have as much oxygen. Additionally, many are going to be subjected to crises as lakes literally run out of oxygen in the summer, called summer kills. And many of you are familiar with this. We're seeing this more and more in our waters, that we're having these summer kill events, in which really run out of oxygen at night in the warmest summers. And lastly, of course, you all know that invasive species are a big issue, and we're losing many fish like walleye from some of our most prized lakes. And this is all a direct prediction of small increases of temperature, because many invasive species, such as the carp I study, do much better at warmer temperatures, while walleye require much cooler temperatures. And that's what this figure is showing here from the state of Wisconsin. There's no question that bass numbers are increasing while walleye numbers are decreasing. This is just basic physiology and how these animals work as with respect to temperature. And of course, when you factor in the oxygen, it's even more challenging. The third part I wanted to bring up is that with increasing heat, we're getting increasing, and I'm sure you're all aware of this, we're also getting increasing stratification or layering of our lakes with reduced turnover. And this is exacerbating the oxygen problem, because the layers, the hypolimnion down below, stays very stagnant. And as it runs out of oxygen, this is the double whammy, nutrients are released, because as you may probably know better than me even, anoxic sediments, it's just how the chemistry works, release phosphorus into the water. So a static lake in a thermocline, which is already, whose fish are already suffering, will start to experience plankton blooms, intensifying with warming and nutrients as a result of these eutrophying systems associated with small degree temperature changes in the summer. Further, it's directly predictable and expected, and it's already happening. Invasive species are doing especially well. Plants like Eurasian milfoil, and lakes will increasingly shift into what's known as a new type of stable state as they slip from one equilibrium point with checks and balances into another. And this is basically shown by this figure here, but everything has its feedback loops and exists in a certain type of balance. So your body does, our society does, our economic systems do, the animals and plants in the lakes do too. As they shift from one state to another, they get locked into it. And that's exactly, unfortunately, what's starting to happen. and what you continue to see. I'm sorry if it's a bit depressing. And the fourth point is that as these, you can see these things basically synergize and add to each other. But as these lakes warm and run out of oxygen, we have the added issue in this area of the world that rainfall and snowfall is expected to increase and push further nutrients off the land, and further leading to a degradation and to things. Importantly, this is very important to understand. You can look at a lake like a ball, and this is called the ball and cup model, but there's a certain resilience to it and resistance to get out of this condition. But once it slips into the other, like with nutrients, then it's very hard to get it out. This is why lakes are so hard to restore. Finally, one more little factoid, which is important to realize, that this, of course, and I showed you the figure, atmospheric CO2 is increasing. Atmospheric CO2 combines with water to form carbonic acid. Like, this is how this is what makes pop tasty, frankly. This low pH is why it's bad for your teeth. And this, of course, isn't going to do very good things, at least for the native fish and plants we have in our present lakes, because they all prefer certain pH limits, and many of them can't go to lower pHs. So that's the bad news. There is some good news. And one of the things is that remember now that we're facing this situation whether we want to or not. There is some actually excellent news. This is one of the reasons I moved to Minnesota. Although I think about a third to half of our lakes are impaired now, a third to half are not. And we have many high quality, we're very blessed, we have many high quality waters that are still doing quite well with relatively low nutrients, good, robust water systems and drainages, and high biodiversity that put up this resistance to change. And these systems, and then I'm showing the complexity of a biodiverse lake here, are to be prized. That's what I'm saying, because not only are they much nicer, but they're going to withstand the threats of climate change much, much better than the old worn out ones that are deteriorating. And additionally, we're very fortunate because many of these very fine lakes, we are fortunate, are highly connected, and they're in a position actually to improve waters to the downstream of them because that's the way they flow. So that's a really wonderful thing. So when we look at this then, and I'm just bringing you back to remind you, this is not really a lecture about climate change and how to prevent it, it's how to deal with it. I'm a realist. We are necessarily, and you as managers are looking at a situation in which the temperatures are going to continue to warm, the lakes will continue to warm up, they will lose oxygen, they will gain nutrients, and they will flood. So, given that we still have many good lakes, and they are often upstream, I think, and this inevitable challenge to them is going to be persistent. My, I guess, plea in a way is to tell you that it's time now, if there ever was a time, to get really, really serious about protecting and preserving, protecting, preserving these high quality lakes in our headwater systems while we absolutely can. These are naturally resilient systems. Let's do this for the entire watersheds that you manage and the fish within them, and for future generations of Minnesotans while we can do it. Let's identify in particular about 5 to 10% of the state's most resilient lakes and identify them as state refuge lakes, in which there would be continued, efforts to reduce development, acquire surrounding lands to protect and manage. Let's do this as a new approach and a new scheme. Not letting outside boats in because they can bring AIS. There is no technology, unfortunately, that can stop this, except not building a boat ramp, which is a pretty easy one. I'm not saying people can't access lakes or use lakes. Of course they can. They just can't bring their own gear with them. That's all I'm saying. And there would be catch and release fishery. And we might identify second and third tier lakes too. And I'm wondering, of course, whether Maud can help me. So again, what I'm suggesting is a new paradigm for managing lakes in Minnesota, or additional one, not to replace what we have, to identify the strong ones so they can protect the weak and work that way. We might consider Lake Itasca a state lake for this purpose. And I'm sure some of you wonder, is this really doable? This is what I hear all the time. Oh no, people won't take these increased regulations that limit or restrict or reduce their access, but not total access to lakes. People don't want to stop building houses around them and releasing nutrients, et cetera, et cetera. Well, it's entirely doable. The thing is, there's already a perfect model in place. 75 years ago, the first marine systems off of Florida, John Pennecamp's system, were identified as undergoing the same sorts of threats we see now, with the exception of climate change, because it wasn't very well identified at that point, except by scientists. And they set that aside because there was all this construction, hotels, people overfishing, too much scuba diving, collecting coral reefs, and they established what was known as a marine protected area. People still access it every day by the thousands. They can just restrict it in the sorts of things that it can do in these areas, and that's a marine protected area. And so successful these have been that there are over 14,000 of them scattered across the surface of the world now, making up 4% of the ocean's surface, with the goal eventually being 10%. It is seen as the best and only hope for marine systems, marine aquatic systems. And I would submit to you that's the same for freshwater. And I just wanted to point out here, this is an example from a marine protected system, but by creating these systems, this is the Merritt Island Reserve, which is actually Cape Canaveral up here, you really can, this is proven, benefit systems way downstream. And this is some data here showing world record capture rates of various sports fisheries, red drum, black drum, spotted sea trout. And you saw up to 10-fold increases in fish captures downstream of this location because it became a naturally balanced and fish nursery, basically, that supplied the entire area. This is well known as the spillover effect. So lastly, what's next here? What's next, I think, which I'm going to advocate for I will hold a workshop on climate change in our waters. I think it is the issue for aquatic biologists and managers for the foreseeable future, unfortunately. The good news is there are ways to deal with this. We would review the threats of climate change and solutions. We'll look at marine protected areas as an example. I teach marine biology. My background is marine. I think there are many, many lessons there. There are many, many lessons, and try and identify a path forward. So what I'm hoping is that maybe Maud can help and participate in this in some way. That would be a wonderful thing to do for all the reasons I gave: invasive species, water quality, biodiversity, fisheries. All these things would benefit from just setting aside at least a few lakes in this state while there's time to protect and enhance the others around it. So thank you very much for your attention. And I guess I sign off now, and maybe I'm around hopefully to collect your comments. Thank you again.